Hello and welcome to the latest installment of the Bic Gardner webinar series. Today we'll be talking about media milling and taking a deep dive into it. My name is John Kowalski. I'm part of the marketing team here at Bic, and our presenter, Mr. Andy Stummer, he is our business line manager for our dispersion line. We are recording this and we'll send out the link to you tomorrow morning for your review or to pass along to any colleagues. Also, we will have time following the presentation for some questions and answers. So if you do have any questions, please log them in the Q&A box located in the bottom right-hand corner of your screen, and we'll get to them immediately after the presentation. So with that, let me introduce and hand it over to Mr. Andy Stummer. Andy, it's all yours, sir.
Yep. Thank you, John. Thank you, and hello, everybody, to our second edition of the Deep Dive. This one is about the media milling. About a month ago, we did the first part that was about the actual predispersion, and this is the second part. So it's a little bit more technical than last time, but you can ask questions at the end, and we'll have some time. We'll cover those very thoroughly. So we got just briefly talk a little bit about the company, give you guys an overview of who VMA is and the relationship with Bic. We're going to just briefly touch on the dispersion process, the pre-dispersion part, what we covered last time, just a very brief couple of slides. We also covered the different types of milling technologies and then lab and production equipment. We also discussed QC, how we're going to control the data, and then at the end we're going to finish up with just showing you some of the different laboratory capabilities that we have here in the US as well as at VMA in Germany. So briefly, the company VMA is a German company. It was founded in 1972 by Mr. Hermann Getzmann and his beautiful wife Elke. Herman is still coming into the company at least once a week just to make sure that they still follow his design philosophy and that the company is running smoothly. It's actually managed by his two sons, Martin and Christian Getzmann. Right now they have about 100 employees all over the world, so it's a very fast-growing business. And they are known for high-end feed mills, basket mills, vertical horizontal milling equipment for the laboratory, pilot, as well as manufacturing. In the US, we started offering manufacturing equipment about 3 years ago. It's been very successful, and we have some really unique technology that will make everybody's life a lot easier when you look at manufacturing. So we'll cover that as well. The first Dispermat actually was introduced in 1973. And one of my very first visits with Bic, I've been with the company about 15 years now, was a company in Charleston, South Carolina, and they imported these machines about, I think, 30 years ago, 35 years ago. And to this day, they're still running the original Dispermat with the original motors, and they have about 10 of them. So pretty unbelievable. Just speaks for the quality. The company is in Germany. Here you can see that building here in the back, the second building. This one is actually the latest addition. So that's where all of our R&D and design center is located, as well as office space on the top. So we have about 8 people in design, and you should know that about 40% of all the equipment that VMA manufactures is custom. So there's a lot of different applications, and so we can meet a lot of different requirements in the milling and dispersion world. Bic has had a strategic relationship with VMA since 1988, and we are the exclusive distributors of these products in North America, US, and Canada. All of the Bic labs are using the VMA product line, so we're very familiar with what we're actually offering here, and we believe it's really good technology. So that's just a brief intro. So there is a different, obviously, types of pigments that we want to disperse, especially in the coatings world. So we're talking about organic pigments, inorganic pigments, there's the functional pigments, and then obviously we'll have a whole line of especially fake pigments that need to be dispersed and maybe even go down to primary particle size and in some applications. So the goal there is, if we do it right, we're going to have an improved gloss. We're going to get better transparency of our coatings. Color strength is definitely a big improvement with proper dispersion, as well as the cleanliness of shade, just among a few of those really important attributes that are critical when we do a proper dispersion. So why are we really doing this? So obviously we want to achieve better wetting. We want to break up these binding forces, these invisible forces called Van der Waals forces. They keep those pigment particles, these agglomerates, clustered together. So the goal is to really break up these binding forces, and then in some cases, ideally go down to primary particle size. That's where we need to do that milling. And that allows us to have just better color strength, gloss, and overall a much better appearance. The result will be we have a lot more efficiency, so we can save costs. We don't need to use as much pigment. Also, our product is more consistent with a more reliable milling cycle. Then we also have, obviously, that leads to formulation improvements, constant particle size, distribution, and finally, we'll be able to upscale much better and easier if we do it right in the lab. Okay? So some of the problems that occur if we don't do it right, so we have poor color or color stability, or even color shapes are possible, the flocculation of our pigments. A lot of people are familiar with that. Sagging, leveling, settling, gloss is not as nice if we do an improper dispersion milling job, and obviously the separation as well. So here are some of the most critical components to proper dispersion. So obviously we want to have stability, to have better color fastness, and to reduce the fading over time. We want to improve our brightness. So this will also give us the best superior color. Our pigment size is critical. Obviously, the smaller usually the better to improve our transparency and color. And obviously, we can reduce our costs by using less pigment or by reducing our particle size. And then obviously viscosity, the lower our viscosity, we're going to have better processing of the material, and that also should lead us to improved particle size distribution as well. Okay, so it's really important to remember that when we talk about dispersing and milling, it's about actually reducing the particle size to break up these binding forces. We don't want to actually destroy our pigment particles, and these agglomerates and these aggregates really reduce to the primary particle size. So when we actually pre-disperse, we actually break up the binding forces of our agglomerates, and then when we do the actual milling part, which we'll cover in detail today, this is when we actually break up the binding forces of our aggregates, and that allows us to really go down to the primary particle size. So it's really the shear forces that we are creating either with our cow's plate in the predispersion process or our media, our beads, in conjunction with our milling rotor, are really responsible for the further de-agglomeration of our aggregates down into the primary particle size, and we call that fine grinding or milling. And then at the end, obviously, we need to use some additives to keep all these primary particles in a suspended state so they don't flocculate out. So that's some of the key points here, what we want to achieve when we mill our product. Okay, so this is just a quick slide showing you different types of pigments that usually are in a lot of different applications, and some are easier, some are more difficult to break up, but the equipment manages to do all of that and with these types of pigments. So the dispersion process, first of all, we have these clusters of our pigments. We call them, these larger clusters, we call them agglomerates, as you can see in the slide right there. And then the next smaller cluster, once we break up these binding forces with our high-speed cow's blade, with the high tip speed, we're able to rip them up and then turn these larger agglomerate clusters into smaller particle clusters. We call them aggregates. Okay, so some customers are happy with just the aggregates, but some customers really want to go down to the primary particle size for the reasons we mentioned before, and therefore we need to do the media milling. So that's done with the media. That's step from the aggregates down to the primary particle size. The reason is simple. With the Kaus blade, we don't have enough shear forces or shear stress that we can put into our mill base, so there is a limit, and it's at some point you're going to reach diminishing returns, and therefore we need to move over to a different milling technique, which is the fine grinding. Okay, so at the end, then once we achieve the primary particle size, then we want to basically stabilize those particles with the right additives. So I like this slide a lot. It shows it, the different steps. So in the beginning, you know, we're going to wet our pigments. We're going to pre-disperse with the Kaus blade to get these agglomerates, these forces broken up to turn them into aggregates. And then when we reach that critical particle size, usually that's between 20 to 30 microns, and then we really reach this threshold where the Kaus blade no longer is efficient enough. Then we need to move over to the media milling, and that's when we use horizontal or vertical bead mills. We'll cover those, and that allows us then to go down to the primary particle size. Okay, so this is a great slide just showing you roughly when we start milling with the bead and when is the stop of what a dissolver can do. So you can see it can go down to 10 microns, but really most efficiently around 20 microns is when you should start to use media mills if you want to really break down to the primary particle size. I say this with the word of cautions because not all applications are equal, and there are some products obviously that disperse easier than others, but most of that we have seen or I've experienced is where once you reach about 20 microns, it's a good time to now move over to media milling. So the dispersion process is though these two parts. So we have the first part is that pre-dispersion part, which is a necessary step for any dispersion process. So you can't really go into a mill without doing a pre-dispersion because if the particles are too large, you're going to clog up your milling system, the screen, or the dynamic gap gets clogged. We see that a lot, so customers want to forego that step, go right into a horizontal bead mill, and that usually leads to a lot of problems. So ideally, it's a must to always start with a good pre-dispersion and then move over to your fine dispersion once you reach those 20 microns we talked about, okay? So there is a whole range of products. We're not going to cover the pre-dispersion product line today. We are more focused on the different types of mills that we have, media mills that allow us to really break down these particles to the primary particle size. Now, what you see on this slide, and these are some important numbers, you might want to write this down. In the pre-dispersion process, our tape speed is recommended to be between 18 to 25 meters per second. This is really a good window to operate in. And then for the fine grinding, we lower our tape speed 10 to 16 meters per second. I've seen also 9 to 15, somewhere in that range. Again, it depends on the type of product you're processing, but these are some good, solid numbers that you can go and then dial it in for your unique process. Okay? So just briefly, what's important when we do the pre-dispersion, just this dissolver disc diameter in relation to our container is critical. We don't want to have a too large of a blade where the vortex is hindered by the distance between the walls. So we want to have about 1/3 of the diameter of our blade, and we can increase it depending on the viscosity of our product and flow rate. So you can visually see what's going on in your container, but I would ideally start with about 1/3 and then progressively get larger. What you want to see, obviously, is that donut right here. If you look inside, you should see a visual, and we call it the visual cue. How well am I processing my material? And then if I have a very solid pre-dispersion process, then I should ideally see this donut being formed around my Kaus blade. Now, again, some materials that are have a very low viscosity. Sometimes it's a little bit more difficult to get a proper donut because the donut collapses very quickly if you don't have the right viscosity. On the other side, if the material is too viscous, then also it can be a flow issue and it's difficult to get a proper donut. But most coatings or pigment dispersions, you should be able to get that donut if you have the right blade diameter and the appropriate tip speed that we talked about, 18 to 25 meters per second. So here, it's just a really good formula. You might want to write that down. It's how you calculate the tip speed. So it's your velocity is a pi, multiply that by the diameter of your blade, and then also multiply that by the RPMs of your shaft. If you want to do this in metric, meters per second, you take everything, the same formula, but you divide it by 60, and that will give you meters per second of tip speed. Okay, so some important things to remember when we optimize our dispersion result prior to milling. So we want to look at obviously how long am I dispersing my material, usually about 15 to 30 minutes, and I should have a pretty good solid material that I can now feed into my milling system. The donut effect, again, is a good visual cue. Tip speed, 18 to 25 meters per second. That's a good window to operate in. Again, the blade geometry plays a role. And then obviously the right type of impeller disc. There's a lot of different shapes on the market. So we have our own designs, but there's many designs out there. You just got to find one that works best for your process. Then how much milling material do I have in my container? We usually recommend about 50% of fill rate. In some cases, you can go a little bit higher. You don't want to go too high, or you're going to end up with product being spilled over your container. And if you don't have enough product, obviously, you're not going to be able to oscillate the blade really well in the container to move it up and down to get to the right sweet spot where you get the best milling action or dispersing action, okay? Then obviously the concentration of my raw materials, how much pigment or fill am I putting in there. We want to keep the temperature as low as possible. If it gets too hot, if I'm doing solvents, for example, you don't want to evaporate the solvents. And also, if you are too cold in some instances, then the material, the viscosity is too high and it doesn't move properly. So ideally, you want to be between 30 to 50 C, somewhat in that range, and then you can properly move the material and get a good dispersion as a result of that. And then at the end, you want to use the right additives, obviously, to improve your wetting, dispersion, and deflocculation. And that also will help us get better results. And then we want to do a Hegman test and see where are we? Are we ready now to move over to our medium mill? And then we decide based on what type of formulation we have, what do we want to do? Do we want to use a horizontal bead mill? Do we want to use an immersion mill, like a basket mill that's a vertical setup? Do we want to use a pop mill? Is it for the lab? Is it pilot scale? What's going on in production? So there's a lot of things that we want to look at before we decide what kind of bead mill we're going to use for our fine grinding process. So here's just some of the differences. What some of them I stressed already before is on the dissolver, we have a limited amount of energy we can put into a mill base without house blade. Therefore, it's the limited shear force. It's really only to deagglomerate our particles, so you never get down to the primary particle size with just a dissolver blade. And it is, again, a very important step. Don't forego it for your entire dispersion process. So you can't exclude it. It's really critical that we do this properly. And if we only use a dissolver, then we're going to have a lot of limitations to our mill base. Just for example, our color strength will not be the same as if I do a proper milling with my media. When I look at the bead mills now, which is my fine grinding, the second part, so I have the ability to put in much more energy because of my beads. I'm now able to really break down to the primary particle size. In some instances, I can go down to sub 100 nanometers. We have applications. So that's done really well with the right type of media mill. And then obviously, all of our product characteristics should see a huge improvement over our first step when we just use a cowl spade or a dissolver. Okay, so here is now the important parts about the milling. So what actually happens inside of the bead mill? So obviously we're going to have our media in there, our pigments are floating around, these aggregates, and we have our different types of beads that are available on the market, and we select the right one. And now these beads are inside of our milling chamber, and the rotor is throwing these around at a very high velocity. So these beads are drifting towards each other, and through that high velocity drifting motion, that's what's actually causing this high shear rate, and that's causing these aggregates to further get reduced to the primary particle size over time. So it's not that we actually want to crush our pigment, we actually just want to break up these binding forces and turn these aggregates into smaller particles without actually destroying them. Of course, there are some applications where customers actually want to just mill for a long time and they actually want to crush their products, like, for example, silica. I have applications where it's a totally different type of milling, but in this case, obviously, you're actually really crushing the small particles and making them smaller. But with respect to our pigment dispersions, we really just want to break up these binding forces, okay? So one component that is, besides of our tips we talked about earlier, 10 to 60 meters per second of our rotor speed in our mill, we also want to use the right type of beads. So when we look at identify good quality beads, what is it? So obviously it's our hardness, right? Don't use glass beads or soft beads. They tend to shard or break up very easily or wear unevenly, so that's not ideal. But more importantly, you want to have beads with a high specific gravity, because that will give us also more kinetic energy. And as you can see already, kinetic energy is really critical in our deagglomeration phase, because if I have light beads, they're going to either increase my velocity by a lot to increase that hammering of my beads, or I just use heavier beads. Therefore, each flow of my beads, as they drift towards each other, it's just gives it a much higher shear rate. Okay, so that's a great slide right here. You can see that. Look, imagine like this nail or a walnut. If I had a very small hammer and I was pounding away at that walnut, or imagine you had a pencil and hammer at the walnut, it doesn't matter how hard you hit the walnut, you probably will never ever break the walnut shell. But if I give you a sledgehammer, it'll probably take it just one blow and the walnut is all broken up. So that's kind of the same idea when we talk about beads and kinetic energy. So use heavier beads, use better quality beads. Don't buy glass beads. They are not good for milling. They break easily. They're cheap, but you're going to have to replace them off. They wear very unevenly, so you can't really upscale all that well because you don't know, okay, are they all the same size? So, I mean, some people filter them out, but it's a very time-consuming process. So we recommend use zirconium beads. You know, there's different grades. Obviously, yttrium stabilized very hard, and these beads were cerium stabilized, and these beads will then allow you to have much better milling performance over just your standard glass beads. Okay, you can already see, like, for example, like the specific gravity, the weight of a zirconium is 6.1 versus a glass bead 2.5. So it's already a much heavier bead and giving you much better milling performance as a result. Okay, and also look at the hardness just here. Hardness also almost 3 times as hard as a glass bead and much heavier, so you get much better performance. Okay, so I like this slide a lot because it demonstrates kind of where actually the actual milling action is happening. So you don't really, again, we're not trying to crush our pigment and destroy it. We really just try to deagglomerate and to break up these binding forces. So here, these particles get broken up in these corners right here. As these beads hit each other and drift towards each other in these corners, that's where the shear force is, the shear stress is the highest, and that's where actually that breakup of these binding forces takes place. Okay, obviously some pigments will get crushed and they will break up. It's law of probability, but you'd be surprised most of the pigments will actually be pushed away, out of the way, when these beads start colliding towards each other. It's like, you know, it's sitting in a bathtub with two rubber ducks and you're trying to squeeze something in the middle. Probably they'll always just try to get pushed out of the way. So it's kind of the same principle with our milling action here in our mill. So here are some of the really important parameters to monitor, to watch what influences the process. So obviously, after a predispersion, the particle size is critical. If you're too large, you're not going to have efficient milling because it's going to clog up your screen or your dynamic gap, and then you're going to have very poor flow through your mill. Again, bead size and bead weight is critical. The bead type, so stay away from the inexpensive beads. Use zirconia beads. Bead volume plays a critical role. Obviously, the more beads I put in, the better my efficiency. And obviously, the shape of my beads is critical. If my beads are not perfectly spherical, if they're oval, they were unevenly, so be very cautious at that. You can buy beads on the market. There are zirconium beads I've seen online for really cheap, but they, when you actually use them in your process and you look at them under the microscope, they're not perfectly round. So maybe the sample you get is round, but then when you start ordering your first batch, maybe they're not all perfectly round as we have seen. So again, the clip speed, very critical to remember that. Product temperature, now when I'm milling, I'm putting in a lot more energy into my mill base than if I'm just using a cow's blade. So that increase in energy that I'm putting in is all going to be transferred into heat. Therefore, by milling, I need to properly cool my milling chamber. If I'm using an immersion mill or a basket mill, I should be able to chill my actual milling basket as well as my container. So therefore, I keep my product temperature in check. The energy input, how much energy I'm putting into my mill is very critical. I can run some mills. I can run with just a certain amount of speed, but I can also set up, for example, OSL mills. I can run them with what's called constant power so that I put in a certain amount of energy into my mill base, and then the machines will automatically adjust the speed they need to always maintain that amount of energy. Then the resident time in my milling chamber, how long is it in there? How many passes does it go through? Do I have a pass-through method, or do I have continuous mode where I'm circulating my product? So there's a lot of different ways I can mill my product, but with an immersion mill, obviously there is no pass-through. It's all in a batch system. So that's just we're going to have to watch what kind of mill we use for the process. And then obviously the milling tool diameter is just as critical in my milling system. The rotor or my milling tool diameter is very critical, just as critical as with my cow's blade. Then obviously the type of material that I'm using. When I'm milling, I can obviously put a lot of shear stress into my mill base. And the rotor, if it's, let's say, stainless steel and I'm making a white product, TiO2, what happens? If I'm using stainless steel over time, you can watch it happening, that mill base will turn gray. Why? Because the milling is a very abrasive process. The beads will wear on your milling chamber and also your milling tool. Okay, so these tiny shavings will end up in your mill base, and if you do a color check, all of a sudden that beautiful white turned into a gray color. And the reason is that was milled with stainless steel components. It doesn't matter if I'm doing carbon black, I can see a difference, but that's very important when I'm milling light or white products. So therefore, always use ceramic-based products, zirconium milling, line milling chamber, and milling tool for white products. And then for dark products, the stainless steel or the silicon carbide is also a ceramic, very, very hard. Good transfer efficiency from our heat. That is an option there as well. Okay, and then obviously the type of media mill. What do we want to use for a process? Do we want to use an immersion mill in our batch plant or lab? Or do we want to use a horizontal mill? So, for example, if I'm if I want to go down, if I'm milling a carbon black and I need to go down to my primary particle size, and I want to go down to, let's say, 100 nanometers, okay? I can't get there with an immersion mill. There's a limit as how small I can mill. So I need to use a horizontal mill to be really able to go sub 500 or 500 nanometers. There is no other way. Also, what is my viscosity like? If my viscosity is very thick or high, and my product is not flowing properly, like it's thixotropic, it just sits there in my container, and I'm immersing my basket mill, immersion mill into my mill base, and I turn it up, then sometimes if the material isn't flowing properly, it just basically sits there, and the product won't flow into my mill. So therefore, I won't have any other choice but to really use a horizontal bead mill, because there I have more options of pushing my product through the milling chamber. I can use a feeding press. I can use different types of pressure. So it's not as critical as with an immersion mill where I actually have to suck my product inside of my milling basket. So, and then basically draw it back out through the screen. So there are limitations and as to what type of system you can use, and not every milling system is the best way for every application. Okay, so many roads lead to Rome, and in some cases we just gotta, in all cases we gotta use the best option. So I want to show this slide because a lot of customers don't realize this, but all of our disper mats, and that's a patented concept, is they are all modular. So and that goes true for our laboratory pilot as well as manufacturing. So I have a base dissolver. Okay, this is the newest one with the latest C technology screen right here. I can accessorize it and I can attach different milling systems. So for example, here I have what's called an air pressure system. This is my vertical bead mill. It attaches right here and turns my disper mat into a vertical bead mill. Or I can turn it into an immersion mill by adding a TML, tourist mill, that's called, basket mill system, onto my same system. So I turned my dissolver into a milling system. That's perfect because I need to use both systems for the proper process. So a lot of customers like that. They're going to do the predispersion on one machine, and then they do the milling on the same machine as well. We have the same concept also for our manufacturing grade. So that's also very unique to the DMA product line. I'll show you a couple of slides of that. Okay, so it's just a bigger slide of the latest disper mat. This here is the AE model, go up to 20,000 RPMs, depending obviously on the size. We may not need that if our blade or milling disc diameter is larger, and we don't need to use all these RPMs, but for very small milling jobs, I need smaller discs, therefore I need to have these high RPMs to get that right tip speed window. And that beautifully allows me to really accessorize it like I showed you on the slide before. So you can see on top here, that's what we call it a DL shaft with that bayonet style clamping system, the quick change system. So all I do is loosen the clamping ring up here and then push down that whole assembly and replace that. Right now it has a cow's blade and put on a basket mill, an immersion mill, okay, all on the same machine. It's a really, really nice concept and it saves you time and money for cleaning, and also you don't have to buy two pieces of equipment. They also have the explosion-proof design. So for solvent applications, if that's something you need, we have EX models also for manufacturing. Okay, so I'm just quickly turn that machine over to a homogenizer and emulsifier, or as a disperser with my cow's bit or the different milling tools. Okay, so how does that milling, that basket mill design really look like? So our design is very unique compared to the competition, and there are some huge benefits to design here. Number one, we want to really cool our milling basket. Like I said before, it's very critical because that's where most of my energy is introduced, and the heat, it heats up very rapidly inside of this space right here, okay? So this space inside of my milling chamber gets filled with my beads. My media is in here. The mill base basically gets sucked in. There's like a vortex wheel on top that's patented. You can see that right here. that actually is designed to basically draw in my mill base into my milling chamber. And then the beads and the milling disc right here will, with the optimized speed, tip speed, will then break up these binding forces. And then on the bottom here, I have a screen. And then outside of the screen, I have another cowls blade right here. So that cowls blade has a purpose of doing two things. Number one, to actually suck my mill base out of my basket through the screen on the bottom, and then, and then outside of my basket mill, and then push it back around. So this is a really good slide here where you can see it. So my media is in here, and then you can see the cowls blade here actually is drawing out my material and then pushing it up to the top, where then the vortex will take over and sucks it back in. So I have a really nice continuous movement of my mill base through the basket, out through the basket, and around in my container top. So very good circulation, and that's very efficient. And then I'm cooling everything with these two rods, so water in and then water out, or cooling fluid in and cooling fluid out. On my production scale machines, I'm actually feeding my beads right here, and then I'm actually, here is for cooling right here, one cooling coming in and cooling going out, and then back here is actually my temperature sensor, where I'm actually measuring the temperature inside of my basket, which is the most critical part, because that's where all my forces are building up the heat. And then below here, you can just see the cowls blade, so it's very nice design. Competition has a screen on the side here. They're closed on the bottom. We believe it's better to do to use this for cooling, and then we also cool the top. So we actually cool the entire basket. We're not just cooling a portion of it. So we have this design is patented with the screen on the bottom, and it's really, really an efficient way of using a basket. Okay, so some of the limitations, obviously, there is that it's a batch system. So if I'm just making batches, then it's great. But if I want to do a lot of volume and I'm used to horizontal mill or three-roll mill, then this might be a limitation, because I can only manufacture what is in my container. So that's the volume that I can do. If I want to go fast and produce a lot, then maybe I need to look at something more horizontal, where I just feed it through, coming out on the other end, and therefore I can produce more volume, maybe faster. The design is really nice because it's very simple. I don't have any bearings. I don't have any real wear parts outside of my milling disc and my screen. So if I look at a horizontal mill, those of you that use those are familiar with all the different parts and replacement and cleaning. It's a cumbersome process. You got to be a real expert at it. And also repairs are much higher, more common on a horizontal mill than I would see on a basket mill. So ideally, if I'm running a lab and I'm producing material and time is of the essence, if the viscosity at the primary particle size requirement allow me to use a basket mill, unless I have to upscale to a horizontal system, then it's also a different story. Then I would probably always pick a basket mill over a horizontal mill for the reasons I just mentioned, okay? But if that's not the case, then, I want to go down to low nanometers, and, my product viscosity is too high for a basket mill, and I want to do a continuous mode, then I probably will have to use a horizontal mill, okay? So on the basket mill now, we also offer a nano kit, but there is a limitation, is you can only properly go down to about 400 or 500 nanometers, and then that's kind of the end of it. Otherwise, we really have to go with the horizontal. Okay, so here's just some different slides showing you the different sizes. So we can go from a half a liter to about 2,000 liters of product. Very easy to change my color, as I mentioned, with that type of milling system. There is also the ability to do vacuum. So there's some benefits to that. When I'm using a vacuum system for my milling, I'm more efficient usually in my milling process. I don't have, especially, with a waterborne product, I don't, want to get rid of foaming. So that reduces that. Imagine like some of these foams, these air bubbles entrapped in my mill base, they act almost like tiny little air mattresses. Okay, so they are buffering all the blows and then causing inefficiencies in my milling step. If I can remove those, I have a quicker and more homogeneous milling, grinding. And so therefore, there's also some advantages through the milling cycle, as well as then afterwards, my product transfer is improved because I don't have any foaming, okay? So it's also very easy to scale up or down if I use a basket mill, and I'm producing with basket mills, very almost one-to-one with our system to do that, okay? This is just an example of a large-scale basket mill combination dissolver. This is also unique to VMA. We call this system a TM. TM is unique in that it combines a dissolver and a basket mill all in one machine. Okay, so here is my dissolver blade back here. It's not installed. So this particular customer is a large-scale dispersion manufacturer out in the Midwest, and they purchased two systems. And they basically first push their container there. They do their predispersion with the cow's blade, and then when they reach the required particle size, then all they do is push a button right here on the control board, and that basket now gets lowered, and this whole thing turns from a dissolver into a basket mill. And now I'm actually milling in my large container, so I don't have to use two pieces of equipment. I can do everything on one piece very efficiently and very quickly. Also imagine cost of cleaning time is way reduced, and also space savings because I can do everything on one machine and not on two machines. Also, we looked at some of the numbers, and we are, with this concept, a lot more competitive than any of the competitors on the market today with what they offer, because you have to buy literally two machines from them, okay? So it's huge cost savings and also efficiency standpoint. So then we have, this is more for the laboratory here. It's a milling system called APS, stands for Air Pressure System. It's a very unique design. Basically, it's great for an R&D lab or a quick test lab where I want to just check some color efficiencies. So here I put in my mill base. In this container, it sits on the stand. On the bottom, I have a drain plug, okay? And then basically a screen is in there, and then I can force my product through that container into the container below when I'm done with my milling. So you can see it on this slide here. So the drain plug is right here, and here is my screen, and that's filled up with my beads. There is a cover, so I can, it's a closed system. And when I'm done with my milling, then all I have to do is plug in an air hose in a socket on top of my lid, pressurize my vessel, open up the drain plug, and bada boom, my mill base now gets beautifully drained into my container below. And now I have a milled product. Beautiful, very easy to clean. All I have to do is put that drain plug back in place, fill this up with cleaning agent, solvent or whatever you're using, and then close it again and run it for a few minutes, and then basically just drain the cleaning fluid out. And you should have really a clean container and beads left back in the container. So very, very nice way of producing small batches up to 7 liters of container size. In one case though, as a custom, we have made for a customer about a system for 6 gallons of material, but it's not easy in larger scales because of the handling of the beads and all that. So this is kind of the limitation, and it's really more designed for a laboratory kind of environment, okay? So not really for upscale or manufacturing, okay? Here's another slide showing you what happens when you open that drain plug and how you push out the material. And there's different type of milling tools available. So this is just a triple. There's single milling discs, double milling discs, also different materials. We have zirconium line milling chambers, ceramic milling tools, chrome. So there's many, many different variants that we offer for different applications. Okay, so here are some of the benefits. Obviously, very adaptable, goes on all of our disc formats, very quick, can do small volumes, very quick to clean. I can use this for a very broad range of viscosity, so I'm not very limited just to either low or high. So it's very nice for many, many different viscosity ranges. I have an ability to mill down into my primary particle size, even nano. Again, ceramic components available, and very easy to handle. And again, it's more for your R&D and QC lab, not really for your pilot or manufacturing. Okay, and then finally, there is the world of the horizontal bead mills that some of you are familiar with. So we offer here a disc format SL. This is the latest one. We also have that in different sizes. And then here we have the disc format RS, also a beautiful machine for your manufacturing and pilot scale needs, okay? So we can either, in a horizontal mill, obviously can circulate through, depending how long the millman material. I can also pass through. So some people actually hook 2 or 3 mills together with different bead sizes. So they basically go through one first and then the second mill with smaller beads and so on until, you know, they reach the right bead size that they want, and basically they just pass through it. And then when it comes out at the end, they just put it into a container and ship the product. The pumping and steering system is all integrated. I can go up to 6,000 RPM with my rotor speed. But again, most importantly, it's about actually my tip speed or the peripheral speed of my rotor. There is, again, different parts, materials available for my milling chamber as well as my milling rotor. Here, it's very critical, again, if I'm doing white materials, use zirconium, ceramic parts. Don't use stainless steel. I know they're a lot cheaper, but it's an absolute must-have for white products, or you're going to turn your product gray. Many different media sizes in standard configuration, and then we also offer a nano kit or a standalone nano system, or the nano kit to upgrade the standard version to a nano, and then you can use much smaller beads, and then allowing you to go down to very, very small particles. Our system is designed with, unless we're talking nano, we have a screen in the nano, a small mesh, 0.1 millimeter or 0.2. But in the standard configuration, we use a dynamic gap. So we don't use a screen, so the dynamic gap basically can be changed depending on our media size, and therefore we don't have the screen, and there is no clogging of the screen, no wear of the screen like some of the competitive machines. So our design is very, very efficient and also really nice to take apart and clean, okay? So then obviously quality control is critical. How do we manage our data? Some people just want to go turn it on and run it and write everything down by hand. That's possible. Some customers prefer a little bit more data tracking and the ability to control the process. So we have that new C technology that allows you to really, give different products a name, recall them at a later time, then run the process exactly the same every single time. I can dial in. I can see my tape speed on the display. I don't have to calculate it. I can see my torque reading. That's an indirect measurement on my viscosity, telling me how is that product behaving inside of my milling chamber. Also, I can read up my temperature on the display. I can run the machine also not only with a certain speed setting, but also with a certain amount of energy that I'm putting in. For example, most customers are familiar with running a process, let's say 5,000 RPMs at 30 minutes. Okay, then the machine will automatically adjust the amount of energy it draws to always maintain the 5,000 RPMs. So that's a good way of doing it. But I can also set up my process to say, instead of running at a constant speed, I want to run with constant power. So that means, let's say I put in 1,000 watts of energy into my mill base. That my machine, depending on the change of my viscosity, will always draw will always adjust the speed depending on my viscosity because I'm always maintaining the same amount of energy. So if my viscosity goes down or my product gets thinner, then my speed will increase because I'm maintaining the 1,000 watts of energy. Okay, if my material gets more viscous during my dispersion process, then obviously my speed will decrease because I'm still maintaining the 1,000 watts of energy. So what's really nice about that is now, if I know exactly when I'm running with constant power and I want to upscale and I know, okay, this material I can process, let's say, in 1 hour with 1,000 watts of energy I'm using for this particular material. Okay, so I can now calculate exactly how much it would cost me to make this material, and then I can upscale that very easily and also know what the manufacturing costs are to make a particular product because I know how much energy I'm using over a certain time. Okay, so that's one of the big advantages of using constant power over just constant speed. Okay, I can also run this with constant torque. So some customers want to just ignore speed and power. They want to look at viscosity only and basically run their milling system just based on a constant torque mode. Okay. I can also send the data over to a computer. Here, I'll show you that here. This is the older iteration of the software called Windis, and here I can track everything in a real trend line, know exactly what is going on with my speed. I mean, what is going on with my temperature, my power, so everything can be seen in a real graphical interface. On the machine itself, I have the ability to program different cutout values that allows me to basically tell my machine if I reach a critical temperature, shut the machine off or run at a different speed. If, for example, if I run with constant power and my machine exceeds a certain speed setting, then I can tell the machine to reduce my power or shut the machine off. So there's many ways I can configure my machine to ensure that the integrity of my milling process stays accurate and I'm not ruining my product because some of my parameters are getting out of range. Okay. I can also do what's called a net power calibration. Net power calibration allows you to basically set all the values to a total 0 point, meaning that the machine does not include any of the power numbers that it's using to operate itself without product in the numbers. So anything that you see on the display when you're doing that power calibration, like the amount of energy you're putting in or the torque value, will be strictly related to your product and not the machine input itself. Okay, so that can also be important if you're upscaling, that you know exactly how much energy is your material really using to process that material. Okay. So then finally, just quickly, we have different laboratory resources in Germany where we can do trials, but also in Wallingford, we have a really beautiful lab with our sister company, the Big Additives Group. We can run trials for you. You can come in and we can demo the equipment on your product and showing you how efficient they are and if they work for your process and help you upscale as well with our capabilities there. So these are the two latest pieces of equipment. Actually, we just got them in last week. So we have the latest AE model up there, as well as the latest SL mill, all with the C technology that I just described. So we'll be able to give you a lot of good data for upscale and processing when you come and visit us. So just an overview, it's really an A-class facility. We're able to show you all the different milling tools that we discussed earlier, the different types of equipment, able to scale up for your production. And the beautiful thing is because it's with our additives business, we can now leverage these synergies really effectively by having a chemist on hand if we need to that helps us with product recommendations to your formula, allowing you to not only select a better grinding process, but also better raw material or different raw materials that will help you to modify your formulation and be more efficient. So that's something that we also bring to the table. We're not just a company selling you hardware. We want to be a full solution provider to all your dispersing and milling requirements. Okay. You can also use the location up there as a seminar place We can talk about that offline. If you're interested in bringing a team of people in, spend a few days, we can also make that happen more of as an educational forum to educate all your chemists on the latest milling technologies and maybe even run your own product and show you the differences between the different pieces of equipment. So, okay, that covers it for today. Thank you, everybody, and hope everybody enjoyed the presentation.
Good stuff, Andy, as always. A lot of it great information. And just a reminder, too, we'll be sending out a link to this recording so you can look at it, you know, again, later, share it with colleagues, pause it, you know, just because there is an awful lot of information. But good stuff, Andy. You did a great job of summarizing it. If people have questions, you bet. If people have questions, please log them in the Q&A box. That should be in the bottom right-hand corner of your screen. We have just a few minutes left here, and you know, we got Andy here as well as some members from our team also on the call to help. So, question in from Selma: what is the smallest volume disperser we offer?
We can go down to 0.05 milliliters. 0.5 milliliters. Smallest one would be either a model CV or an AE, CA model that we offer. They are very small volumes.
Yeah, great.
But if somebody's interested, they can reach out. I'll do a Teams meeting, and I'll walk you through the different products that we offer. But we'll have very, very small scale apparatus.
Great. And, you know, and to that note too, if you do have questions after the fact, when you receive the marketing email with a link to the recording, feel free to just hit reply to that. It'll come to myself or my colleague Sherry, and we'll get it to Andy or the appropriate technical person to help you out. So don't be afraid to reach out. We're here to help.
So if somebody on their own time wants to go on dispermat.com, it's a great website with all of our latest products. So just go and there's a tab on top. It'll show you the different product categories, and then you can go in and basically say disperser or dissolver, and then you can click on the different models we have, and there is a table showing you exactly the different sizes for each of the models that we offer in terms of product volume.
Great, very helpful, very helpful. Any other questions out there? You're welcome, Selma. Thanks for joining us. We can give it another minute or two here to see if there's any other questions or any other comments someone may have. You know, we're just looking to publish our kind of second half of the year webinar schedule. So, you know, Andy's doing a few more on dispersion, on media milling, on a bunch of, you know, dispersion business line products, new technologies, things like that. So stay tuned for those invites. Those will be coming out in the next little bit, and that'll kind of round out the year, and also look, because we do continually add programs and add learning opportunities to help. So we'll make sure you're informed of that. So with that, I think we will conclude. Appreciate your time and expertise, Andy. Great resource, and we're lucky to have you here at BitGardner. And,
thank you.
You bet, and thank you for everyone. Sorry, go ahead.
No, glad to be part of that team. Been 15 years, very exciting. And what's really great is that to see all the new technologies that EMA is coming out with. You know, I can't stress enough, like just this year alone, we introduced some really unique technologies with that seed technology, as well as that new TM we offer in the U.S. for manufacturing scale. Some outstanding products help you really be more efficient, not only in your lab, but also pilot and manufacturing. So I already got some feedback from customers that have some of the production units, and they are so happy with the quality performance and also the amount of money that they are saving, just being able to mill more efficiently. It already is translating into real dollars. So great stuff.
Excellent. All right. Thank you for everyone in attendance, and stay tuned for that email coming out tomorrow morning with the recording, the link to the recording. And we look forward to seeing you on future webinars by Big Gardener. Thank you.
Thanks, everybody. Have a good week. End.